All right, we use these large language models pretty much every single day. But have you ever stopped to wonder how they actually work? You know, how did they get from your question to this perfectly formed paragraph? Well, today we're going to pull back the curtain and look at the actual mechanics behind the magic. Let's get right into it.
It feels like magic, doesn't it? You type something, hit enter, and boom, an answer starts flowing onto the screen. It seems totally seamless. But that smooth output is hiding a really fascinating and pretty complex process. We're going to break down exactly what's going on in that tiny moment between your prompt and the model's response. So if you remember just one thing from this, let it be this. At its very core, an LLM isn't thinking or understanding like a person. Nope. It has one single job. Look at all the words so far and make a really, really good guess about what the very next word, or what we call a token, should be. That's it. Everything, and I mean everything, flows from that one simple but incredibly powerful idea. But okay, how does it make such good guesses? It's not just pulling words out of a hat. The real breakthrough, the thing that makes modern LLMs so powerful, is a mechanism that lets the model focus. And that secret ingredient? It's something called attention. This is the key idea right here. Just think about how your own brain works. If I say, the capital of France is, your brain instantly knows that capital and France are the important words. You don't really care about the or of. Well, the attention mechanism is what gives the model that exact same superpower. And you can see just how huge of a leap forward this was. Older models were kind of clumsy. They just treated every single word in the sentence as being more or less equal. But with attention, modern LLMs can zero in on the keywords that are absolutely critical for figuring out what comes next. It's like the difference between hearing a mumbled sentence versus hearing it with crystal clear emphasis on all the important parts. Of course, this attention span isn't infinite. It has a limit, and that limit is called the context length. The easiest way to think about it is as the model's working memory. It's the maximum amount of information, your prompt plus the response it's writing, that it can hold in its head at any one time. And there's always a trade-off here, right? A longer memory is more capable, but it's also way more expensive to run. So we know the model predicts the next token by paying attention, but how does that actually happen under the hood? Well, the best way to visualize it is as a two-stage assembly line, a prefill phase and a decode phase. Let's see how that works. So, phase one, prefill, is all about getting ready. The moment you hit enter, the model grabs your entire prompt, chops it up into tokens, turns those tokens into numbers it can work with, and then processes all of them in one massive parallel push. This is the heavy lifting. It's like reading and thinking about an entire essay question before you even start writing the first word of the answer. Then, right after the prefill comes the decode phase. This is the part you actually see happening on your screen. For every single new word, the model looks back at everything, your original prompt plus every word it's already written, calculates the odds for what could come next, picks one, and adds it to the end. And then, it does that entire process all over again for the next word. And the next. It's this one-at-a-time, step-by-step process. Now that step where the model chooses the next token, that's where things get really interesting. See, it doesn't always have to pick the most obvious predictable word. We can actually tweak its level of creativity. And this brings us to what's known as the art of sampling. Probably the most common way to control this is with a setting called temperature. Just think of it like a creativity dial. If you turn the temperature way down, the model gets really conservative. It'll always pick the safest, most probable word. But if you crank that temperature up, you're encouraging it to take some risks, to pick some less likely words, which can lead to more creative, surprising, and sometimes, kind of weird results. And beyond temperature, you have a few other strategies. Greedy sampling is the most basic. It just picks the number one most likely word every time. Super safe, but it can get boring. To spice things up, you can use top K, which tells the model, hey, pick from, say, the top 5 best options. And then there's top P, which is even more dynamic. Each of these gives the final text a slightly different personality, from robotic to really creative.
Okay, so the theory is all well and good, but actually running these giant models in the real world, that brings up some massive challenges. So let's talk about what the engineers who build these systems really care about: performance, speed, and efficiency.
When you're putting an LLM into an actual product, you're in this constant juggling act between these four things. How fast does that first word pop up so the user doesn't think it's broken? How quickly does the rest of the text stream out? How many people can use it at the same time? And the big one, how much super expensive GPU memory does this whole thing eat up? Out of all of those, the time to first token is just absolutely critical for the user experience. You know that delay you feel right after you hit send? That's what this measures. And it's almost entirely controlled by that big, heavy-duty prefill phase we talked about. Getting this number under a second is what makes an app feel instant and alive. So, how do we make all this faster, especially that word-by-word decode phase? Well, one of the most important tricks in the book is something called the KV cache. Remember how the model has to look back at everything for every new word? The KV cache is basically a cheat sheet. It's a clever way to store the results of all those past calculations so the model doesn't have to do the same work over and over and over again. But, of course, there's no free lunch. There's a trade-off. The upside is huge. Using a KV cache makes generating text way, way faster. That's our time per output token, because you aren't starting from scratch every time. The downside, you have to use up some of that precious GPU memory to store the cache. But honestly, for pretty much any real-world application, it's a trade-off you make every single time. It's a no-brainer. So let's just quickly recap everything. At the end of the day, it all boils down to one simple task: predicting the next token. The magic ingredient, attention, lets the model focus on what's important to make that prediction. The whole process runs on a two-phase assembly line: prefill, then decode. We can act as a creative director using sampling strategies like temperature, and behind the scenes, smart optimizations like the KV cache are making it all run fast enough for us to actually use. And that kind of brings us to what's next. We're already seeing models with context windows, that working memory, stretching to 1 million tokens and beyond. But in technology, whenever you solve one problem, a new bottleneck always seems to pop up. So I'll leave you with this to think about. As our model's attention spans become practically infinite, what's going to be the next great challenge we need to solve?